So today we are going to be talking about the concepts of instantaneous power and average power in steady state sinusoidal systems. So let's consider a source. Does not particularly matter if it is a current or voltage source connected to everybody's favorite generic element, the linear black box network. So this linear black box network could be representative of literally any circuit or component formed of resistors, capacitors, inductors, and sources, either independent or dependent. Let's say that there is a sinusoidal voltage V of t that appears across the terminals of the linear black box network, and there's a sinusoidal current I of t that's flowing into the linear black box network. And let's state specifically that V of t is of the form Vm cosine omega t plus some phase angle theta v. And I of t will be of the form Im cosine omega t plus some phase angle theta I. The instantaneous power which is the power as a function of time, P of t, absorbed by this linear black box network, is what? Do you guys have any idea what the power might be? Very basic level. I times V. Always, 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 the power is simply I times V. Okay. So this is going to look like Vm cosine omega t, plus theta v multiplied by Im cosine omega t plus theta I. Because I'm multiplying these two sinusoidal functions together, I'm going to use one of the trig identities that I introduced to you guys a couple of days ago. I'm going to write it here in blue. Cosine of angle 1 times cosine of angle 2 is 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. So in this case, angle 1 is the entirety of omega t plus theta v, and angle 2 is omega t plus theta I. So if we apply this trig identity, what we're going to wind up getting is 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. So this is the generic form of the instantaneous power absorbed by any linear thing, okay? It obviously requires us to know the magnitude of the voltage drop across whatever we're trying to find the power that's being absorbed by, the magnitude of the current that's flowing through whatever we're trying to find the power absorbed by, the phase angle of the voltage, and the phase angle of the current. So this generic equation works for any linear element or linear combination of elements. So this is our starting point, okay? If you remember any one thing from today, this equation should be it. Everything we're going to do past this is effectively special cases that will allow us to know, need to know less information in order to get the same result. So before we move along to those special cases for resistors, capacitors, and inductors, I want to look at what this waveform looks like as a function of time, okay? So here is our time axis. Here's our instantaneous power on the y-axis, okay? So let's look at this first term here. So 1/2 is a constant. The magnitude of the voltage is a constant. The magnitude of the current is a constant. The phase angle of the voltage is a constant, and the phase angle of the current is also a constant. So this whole first term here is effectively a constant value, on top of which we are adding the sinusoidally varying part on the right-hand side, okay? So we have a DC component over here on the left and an AC component over here on the right. So if I were to plot this, it would look something like this. Here I have my DC level of power, and then I'm going to put an AC signal superimposed on top of it. So something like this. So here is P max, let's call this PDC, and down here is P minimum. So if this is the absorbed power, or if this graph represents the absorbed power of a linear network, we can observe a couple of things. First, exactly half of the time the waveform is above that DC value, and exactly half of the time the waveform is below the DC value. So what does the DC value represent? The average. So the average power is literally just the DC component of the instantaneous power. Okay. We'll mathematically define it in a little bit, but we're going to get literally the exact same result by just inspecting this graph. Okay. So there's a couple of really one other particularly interesting thing here. What do these two sections that I've indicated in blue represent? Anybody have any thoughts? So what does it mean when the absorbed power is negative? It's supplying power. So in a steady state sinusoidal system, anytime there are inductors and capacitors present, we should see some portion of the instantaneous powers waveform have negative values. So this is the energy storage elements acting as sources and supplying energy back to the remainder of the system. Okay, so this is an expected thing. All right, now let's get into details specific to resistors, capacitors, and inductors. So for a resistor, and I'm going to be pulling up some information that we developed a couple of days ago in our phasor relationships portion of the lecture. We know that the magnitude of the voltage, Vm, can be expressed as R times the magnitude of the current. And we know that the phase angle of the voltage and the phase angle of the current are the same thing. Okay. Using these results, we're going to start with P of t is equal to 1/2 Vm Im cosine theta v, minus theta I, plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I, and substitute in these relationships, and we can find that we'll be able to express the instantaneous power absorbed by a resistor only in terms of voltage quantities or only in terms of current quantities. Meaning, if we know the voltage drop across the resistor or the current flowing through the resistor, we have enough information to calculate the power. We will no longer need to know both quantities. So we're simplifying the amount of analysis that is necessary. Okay. So expressed only in terms of voltage quantities, this is going to look like 1/2 Vm squared over R. So I'm simply replacing the quantity Im by Vm divided by R. And then we're going to have cosine theta v minus theta I. So if theta v and theta I are the same thing, we're taking the cosine of 0, which is 1. So we have a constant term times 1 plus that same 1/2 Vm squared over R cosine twice omega t plus twice theta v. So this is what our instantaneous power looks like, expressed only in terms of the quantities related to the voltage drop across our resistor. For current quantities, we're going to have 1/2 Im squared times R times 1 plus cosine twice omega t plus twice theta I. So over here on the right-hand side, I'm going to make a plot to depict what we should see for just resistors. So here's T, here is PR of T, the instantaneous power absorbed by a resistor. So our average value corresponds to 1/2 Vm squared over R, which is the same as 1/2 Im squared times R. And what we'll find is that our instantaneous power waveform is going to look something like this. So obviously half of the time it's going to be above the average value, half of the time it's going to be below the average value. It's going to oscillate between its maximum value and 0. We know for a fact that the resistor is incapable of storing any energy or storing any power. So we should never see its value fall below the horizontal axis and give us a negative result. Okay. All right. Now let's talk about an inductor. So what are the relationships for an inductor? The magnitude of the voltage Vm was equal to omega L times the magnitude of the current. And we know that theta V is equal to theta I plus 90 degrees. So once again, we're going to start with our generic equation. 1/2 Vm Im cosine theta V minus theta I plus 1/2 Vm Im cosine twice omega t plus theta V plus theta I. And we're going to modify this based on the relationships that I've written above. So expressed only in terms of our voltage, we are going to have 1/2 Vm squared over omega L. Now let's look at this cosine theta V minus theta I part, okay? So if theta V is equal to theta I plus 90 degrees, theta V minus theta I is theta I plus 90 degrees minus theta I. The theta i's cancel each other out, and we're simply taking the cosine of 90 degrees. What's the cosine of 90 degrees? 0. So that tells us that there is no DC part of the instantaneous power absorbed by a inductor. Exactly half of the time it is absorbing power in a steady state sinusoidal circuit, and the other half of the time it is supplying that power back to the system. Always just going back and forth. So we're going to move over to the right-hand side of the expression, understanding that the DC part is 0. We're still going to have 1/2 Vm Im, which looks like 1/2 Vm squared over omega L. Now we're going to have cosine twice omega t plus twice theta V minus 90 degrees, expressed only in terms of the current. We're going to have 1/2 omega L Im squared cosine twice omega t plus twice theta I plus 90 degrees. Graphically, should look something like this. Exactly half of the time the instantaneous power is above 0. Exactly half of the time the instantaneous power is below 0. Yes, Hayden. So if theta V is theta I plus 90 degrees, theta I could be written as theta V minus 90 degrees, right? So theta V plus theta I is going to be theta V plus theta V minus 90 degrees, or twice theta V minus 90. And then in terms of the current, it winds up being a positive sign. So it's just manipulating this relationship to express everything only in terms of theta V or only in terms of theta I. We'll see something very similar for the capacitors in just a moment. So for a capacitor, our relationships are the magnitude of the current is equal to omega c times the magnitude of the voltage. And our phase angle theta I is equal to theta v plus 90 degrees. Starting with our generic form for our instantaneous power. We have 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I, expressed only in terms of the voltage. This is going to be 1/2 omega c Vm squared. So when we do theta v minus theta I this time, it's going to look like negative 90 degrees. The cosine of negative 90 degrees is still 0, so we have no average value. We're going to have cosine twice omega t plus twice theta v plus 90 degrees. In terms of our current, we're going to have Im squared over omega c cosine twice omega t plus twice theta I minus 90 degrees. And this graph is effectively going to be exactly the same thing as what we would see for the inductor. Half of the time it's absorbing power and half of the time it's supplying power. Average value of 0. Okay. We are going to talk more about what the implications of the instantaneous power absorbed by an inductor and the instantaneous power absorbed by a capacitor having 0 average power. We'll talk about that more. Let's see, what day of the week is today? Friday? Next Monday and next Wednesday, we're going to talk about the concept of power factor and all that kind of jazz. I'm bringing this up because some of you might argue, well, what's the point of having them if exactly half of the time they're absorbing and the other half of the time they're sending it right back? If we didn't have inductors and capacitors in our steady state sinusoidal systems, we would actually suffer from blackouts constantly. The temporary energy storage is very, very important to keeping our grid up. So anyway, all right, so we are going to do an aside here. This is largely to help you guys with your homework stuff because you're going to be asked to find the average value of signals and all that kind of jazz. And then we're going to work an example problem. So if I scroll up here and we look at this graph, we intuited effectively that the DC component of the average power, or excuse me, the DC component of the instantaneous power is the average power because half of the time it's above that level and half of the time it's below that level. Now we are going to develop a more mathematically rigorous explanation that gives us literally the exact same result. So to facilitate this, we're going to have to start with how to find the average value of any periodic function, okay? So let's say that I have the following function that is defined as x of t. And it is a series of triangular pulses like so, propagating in perpetuity, okay? Is this a periodic function? Let's start there. Sure, it repeats itself. If we call this point in time t, 1 period, then this would be 2t, 3t, etc. How do we find the average value of this periodic function? You guys should have covered this in your calculus classes, but if not, it's okay. So x average is going to be equal to the integral over exactly one period of x of t, and then we divide that integral by the duration of the period. So the average value of the function is the integral of the function over one period divided by the duration of the period. Everybody okay with that? Does that mathematically make sense? Hopefully it's familiar, maybe not something you've had to use in quite some time, okay? So average power then is going to be 1 over t times the integral over exactly one period, excuse me, of 1/2 Vm, sorry, Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I, all of this with respect to time, where I've simply substituted in our instantaneous power equation, P of t, which is a periodic function. Now, I can split this integral up into two parts to make it a little bit easier to process. So I'm going to have 1 over t times the integral from 0 to t of 1/2 Vm Im cosine theta v minus theta I dt plus 1 over t times the integral from 0 to t of 1/2 Vm Im cosine twice omega t plus theta v plus theta I. Anybody have any problems with me splitting that integral up into two parts? All right. So we're going to look at the right-hand side first. Sorry, I'm boring you guys already. I promise we're almost finished, okay? So what does this right-hand integral represent? It is the integral of a sinusoidal function over exactly one period. What should that be? Let's draw a picture. The fact that you guys didn't answer immediately troubles me very slightly, but it's okay. I'm a jackass. So this is the AC part of our instantaneous power as a function of time. This is one period, right? One cycle of our power waveform. I integrate over one period. What do I get? 0, because exactly half of the time it's above 0 and exactly half of the time it's below 0. So this whole thing right here goes to 0. Anytime we integrate a sinusoid over an integer number of periods, the answer will always be 0. I'm bringing that up because we're going to use this exact same relationship tomorrow. So just as a heads up. So our average power is then defined by everything over here on the left-hand side. Well, as we discussed earlier, all of that is a constant. So what happens when I integrate a constant over a fixed duration of time and then I divide by the time. I get the constant. So our average power comes out to be 1/2 Vm Im cosine theta V minus theta I. The exact same result we got by effectively intuition of looking at our graph is the exact same result we get actually applying math, okay? Which is great. All right, so that is enough out of me regarding all of this terrible math and stuff. So you guys have an in-class assignment to do. I want to make you aware of a couple of different problems that I see very, very regularly, okay? So I believe you're asked to evaluate. Let's work part of problem number 1 together. This will make both of our lives easier. So let's open, not senior design stuff. Let's see, 221. The last time I updated these was spring of 2020, I think. We are on in-class assignment number 22. We're not going to look at problem 1. We're going to look at problem 2. Okay. So problem 2, we have 3 circuit elements that are connected in parallel. We have a current source, a 1 kilo ohm resistor, and a 15 millihenry inductor. So in the time domain, we are going to have Is of t in parallel with our 1 kilo ohm resistor in parallel with our 15 millihenry inductor. Even though we are asked to calculate the instantaneous power, which is a time domain quantity, we are going to do all of our required circuit analysis in the frequency domain because we don't want to do 45 minutes of trig. Okay, so I'm going to convert my circuit into the frequency domain. So my 100 milliamp source is now going to be 0.1 angle 0 degrees amps. Everybody okay with me representing 100 cosine 2 times 10 to the 5 t milliamps as 0.1 angle 0 degrees? Anybody not understand where that phasor relationship came from? All right, nobody is willing to admit they don't know where it came from, so we'll move along. Our 1 kilo ohm resistor is going to continue to look like a 1 kilo ohm resistor. Our 15 millihenry inductor will look like a J3 kilo ohm resistor if my mental math is correct. 2 times 10 to the 5 times 15 times 10 to the minus 3, I believe, comes out to be 3 times 10 to the 3. Okay, so this is our circuit, and we want the instantaneous power absorbed by each element. So I am going to define phasor voltage V. Okay. Positive polarity on top, negative polarity on bottom. I think I'm about to sneeze, so give me just a moment to either get over it or sneeze. Okay, I think it's passed. So I am choosing to solve for this phasor voltage V because if I know the phasor voltage V, I have all of the information I need to calculate the instantaneous power absorbed by the resistor. I have all of the information that I need to calculate the instantaneous power absorbed by the inductor. And I have 97% of all of the information I need to calculate the instantaneous power absorbed by the source. I say I don't have 100% because since I'm looking for absorbed power, I technically need to know what the current flowing in the opposite direction is. I would just shift 1 angle 0 to, or 0.1 angle 0 to be 0.1 angle 180 degrees. And now I know everything I need to know, okay? So let's calculate this quantity V. Anybody have any thoughts on how we might do it? You're not wrong, but it's not the most efficient route possible. Oh my God, you're making it even harder. There we go. Ohm's law. Thank you, Zachary. We have a current source in parallel, or excuse me, a current source in parallel with two impedances in parallel. So just I times ZEQ gives us what we're looking for. Why make it any harder than that? Thank you for the correct suggestion. So this is going to look like 0.1 angle 0 degrees amps. And then we're going to have 1 kilo ohm times J 3 kilo ohms over 1 plus J 3 kilo ohms. I'm going to throw this in my calculator real quick. So 1 times 3i over 1 plus 3i times 1,000 times 0.1 94.868 angle 18.435 degrees. Okay. All right. So I'm only going to do one of the instantaneous power calculations for you. So tell me which one you want me to do. The inductor. All right. So for the inductor, let's do this in purple. We know that the instantaneous power absorbed by an inductor in terms of the voltage is 1/2 Vm squared over omega L times the cosine of twice omega t plus twice theta v minus 90 degrees. Okay. So this is going to look like 1/2 times 94.868 volts squared divided by omega, which is 2 times 10 to the 5. L was 15 millihenries. And then we're going to have cosine of 2 times 2 times 10 to the 5 radians per second. We're trying to find it at a specific time, which is 10 microseconds. So that is 1 times 10 to the minus 5 seconds. I'm going to leave us some room here to explain. I'll explain why in just a moment. Then I have twice theta v, so that's twice 18.435 degrees minus 90 degrees, and I'm going to close this thing off. So the most common mistake that I see you guys make is, since we're evaluating this at a very specific instant in time, 2 times omega times t gives us an angle in radians. Our phase angles are all in terms of degrees. If we do not convert one of those into the other one, we are not doing our cosine evaluation correctly. I typically convert the omega t bit into degrees by simply multiplying by a factor of 180 degrees over pi radians, so that I have the cosine of some angle in degrees plus some other angle in degrees, and all my math will work out correctly. I'm going to break this up into 2 discrete portions here. So let's see, answer, and I'm going to store that as A, just for the sake of argument. So I'm going to have 1/2 times, oh, that's annoying. Well, oh well. The TI calculators, you can literally do the magnitude of your complex number, so you can just store it as something and then just say the magnitude squared. But it doesn't look like this particular Casio can do that, so I'm going to have to be a peasant and type numbers instead of doing it the way that I wanted to. I'll survive. 94.868 squared divided by 2 times 10 to the 5 times 15 times 10 to the minus 3. So that comes out to be effectively 1.499998. So this would be measured in watts. Then I have this big horrifying thing. So the cosine of 2 times 10 to the minus 5 times 1, excuse me, 2 times, that should be positive 5. Uh, 1 times 10 to the minus 5 times 180 over pi plus 2 times 18.435 minus 90. I get 0.9976. If I multiply these two things together, so times 1.49998, I get, hold on. Sorry, because my calculator was in complex mode, I didn't notice that I had 0.9976 angle 180 degrees, which is the same thing as negative that number. When I multiply these two things together, I get PL at 10 microseconds to be 1.496 angle 180 degrees or negative watts, and seems pretty dang close, a little bit of rounding error. Okay, so that was the biggest pitfall that I wanted you guys to see. If you don't remember to include that conversion factor, you are never going to get the correct answer. So I'm warning you very specifically to include it. Also, not trying to criticize anyone's calculator efficiency, but if you try to put this all in one go, there's a lot of opportunities to make simple mistakes. So I personally split it up just so I can make sure that things make sense. All right, that's enough ranting out of me for today. Work on your in-class assignment and I will assist you if you feel you need it.